Hello everyone, welcome back to the channel. This is Dr. P Aerospace. Today we're going to be wrapping up our discussion on the conservation of mass by doing one more example problem. And this example problem in particular is very evil, and it caused me so much pain. So we're going to try to readdress this and hopefully work through some of the nuances of these deformable control volumes. So if you have any questions about kind of where we are and where we came from with this video series, check the link in the description and that'll kind of show you the path if you're curious as to how you can kind of get to this point in solving these kind of questions. Okay, so let's jump into it. Two very long parallel plates of length 2L are separated at a distance b. The upper plate moves downward at a constant rate Vp. A liquid fills the space between the two plates and is squeezed out of the sides. Determine the mass flow rate and maximum velocity if the velocity is uniform and if the velocity is parabolic. Okay, so first step, always write out your assumptions. Oops, my pointer always does this. There we go. Okay, so assumption number one, let's look for the first hint. So it says we have a liquid here, so we can once again assume incompressible flow. And next, let's draw out our control volume here. Basically the region between these two plates, where our upper surface is coming downwards with respect to time. So we definitely can assume we have a deformable control volume. And then last assumption is just based on the geometry we're working with. I think we can assume we're symmetric about our y-axis, where our y-axis is, or I should say our axes in general, the positive directions are like this. So about our y-axis here, we are symmetric on both sides. And I should say symmetric velocity profile on both sides. Okay, so we have our assumptions. Now we can go into conservation of mass. And let's write it out. Del over del t, integral over cv, rho dv plus our flux term, so bcs, rho times our velocity dotted with our unit normal vector times dA equals to 0. Using our first assumption, we have incompressible flow, so we can knock out this pesky density term here and rewrite it out as del over del t integral. Actually, technically, we can just write this as a total derivative here at this point. So this will just be, because dv is the only thing left in this integral for control volume here, we can technically just write this as dv over dt plus, we have two control surfaces here. We have control surface 1 on the right and 2 on the left. But because they're symmetric, I'm actually just going to say, we can multiply this term by 2. And this will just be v dot n times dA equals to 0. And this term should be pretty familiar. This is just our volumetric flow rate. So to keep things simple, at least for this starting point, I'm just going to rewrite this as q dot. So we would have dv over dt plus 2 times q dot equals to 0. And then after that, we can put our negative or our q dot on the other side, so it'd be like this. And then lastly, we have to find out what dv is. And again, this is kind of where struggle number one starts. Always trying to find what dv is. So let's use this pen here and go up to the top right and try to find out what this is. So one thing to note is that we are working in 2 dimensions. In the last problem, in example problem 4, we had 3 dimensions. We had a conical region that was in 3D space. This one is explicitly 2D. So we're going to assume that our volume and our area are basically normalized by our width into the page. So dv would actually be written as dv over w, and dA would be written as dA over w per unit width. So in this case, our dv per unit width of our control volume would be our length times our height. Our length is just 2L, and our height is B, but we're going to write it as dB because B is changing with respect to time. So our differential volume is 2L times dB. So let's basically combine everything. And we can get that we have 2L times dB over dt equals -2 times q dot. Okay, and then we need to find out what dB over dt actually is. So if we look to our question here, we see we have a velocity of the plate coming downwards. So let's take a little side right up here. Our VP is going in a negative y direction, so negative VP is just going to be equal to change in distance over change in time. So change in, let's say, actually, let me just not get confusion there. Let's just write it out what it actually is. Our distance here is dB, that's the change in distance that our plate is moving, and our time change is just dt. So that's essentially the substitution that we can make into this term right here, which allows us to write an equation in terms of the velocity of the plate. So then we have our final relationship. This will be 2L times negative VP equals -2 times q dot. Our negative signs will cancel out, and we get positives. We also can cancel out our 2's. They would divide out. And we're left that the mass flow rate going through a single surface, this would be technically surface 1, that would be equal to L times VP. Now, if we wanted to write the total volumetric flow rate between both sides, we just multiply by a 2. So Q dot total equals to 2 times L VP. And then the question is specifically asking us for the mass flow rate. So we can write that M dot total is equal to 2 L VP times rho, because Q dot times rho is just M dot. Okay, so we have our total mass flow rate for our system. We also have our individual mass flow rate for each side, which would just basically be this divided by 2, or L times VP times rho. And then from here on out, we can start working on trying to solve for these exit velocities. Okay, so let's get to part A. I'm just going to rewrite our mass flow rate that we had found here. So mass flow rate, I'm going to say out of surface 1 is equal to rho times L times VP. And this mass flow rate, just to clarify, after we shrink our control volume down with time, the integral form of conservation of mass gave us how much total mass has to be flowing out through the vertical face phases 1 and 2. And this is a global constraint. And it's something that has to be satisfied no matter what. That's what we had found from the conservation laws. Now, at the same exit phase that we're interested in, say exit phase 1 here, by definition, the total mass flow rate going through exit 1 would just be equal to integral of rho v dot n dA. And technically, we can set these two equal to each other because they are the same thing. So we would have rho LVP equals the integral, and this is again, for part A, we're assuming the exit velocity is uniform. This would be rho times V dot N dA. We can cancel out our rows here. And let's see, so we have LVP equals, after we do the dot product here, we end up with a positive value outside of our integral because we have an outflow value. And after the dot product, we have a scalar. dA technically is changing with time, but in this case, we can just write it as b of t. So basically, this would just be v1 times b of t. And we're only writing area as kind of one quantity here because I had mentioned before, everything is per unit width. So dA is technically per unit width already. And finally, we can see that our velocity for surface 1, which I'm going to write as u1, is just equal to L times Vp, all divided by B of t. Okay, so this one wasn't too bad. This one was not like a super crazy challenging part. A lot of people get confused with this kind of relationship here. The m dot 1, which is the kind of global constraint that we found from the conservation of mass relationship, and then we're just kind of setting it equal to itself again, kind of. Um, this can be confusing for a bit of people, but again, this was global. This was found with conservation of mass with integral analysis. This is the global constraint. And then when we look at just single surface, like surface 1, we can say like the formal definition of mass flow rate is just equal to kind of this quantity here. So technically we can set them equal to each other. And then we can solve for our uniform velocity at our exit. And this would be for for surface 1. Technically, this would be the same for surface 2 as well. Okay, so we have a lot of empty space here, but just to keep things clean, I'm just going to go to the next page here. Maybe I'll write up here as well. So as a reminder, m dot of surface 1 is equal to rho L times Vp. This is our global constraint of mass flow rate coming out of surface 1. So for a uniform mass flow rate, it was pretty easy, which we see on the previous page here. Our kind of U1 is constant. It's not varying with Y, it's just a fixed value. So we really didn't have to get into the weeds too much with the mathematics here. But for a parabolic velocity profile, our velocity is actually going to be a function of y. Technically y and t, right? Because our plate's squishing the region with time and our y value of our velocity profile is changing. So this is where things can get a little bit complex. Now, the general form of a parabolic velocity profile is something like this. C1 plus C2 times y plus C3 times y squared. So now our goal is to basically find out what these constants are based on our kind of domain of interest and determine what the velocity profile is. And after that, we can solve for our max flow rate, or max velocity, excuse me. And I want to kind of point out as well, I didn't explicitly point out that our max velocity was fixed here because it's pretty assumed. When you have a uniform, mass flow rate coming out of a surface, it's a fixed value, so your maximum value is constant. But anyways, getting back to this. So we have these constants here, and we have to use boundary conditions to solve for them. So I'm going to write our boundary conditions in a different color here. And I'm going to write the boundary conditions down here. So boundary condition 1 at, so say this is y equals 0, assuming that y is kind of going up here. So at y equals to 0, we can say that our velocity v or u of y is going to be equal to 0 because of the no slip condition. For boundary condition 2, this will be at y equals to b over 2 at our midpoint. U of y is actually just going to be equal to our maximum value, which we can kind of see in this velocity profile here. And then boundary condition 3 will be at y equals to b, u of y would be equal to 0, again, due to the no slip condition at the upper surface there. So let's apply boundary condition 1 here to start solving for some of these constants. So that would be, so u of y equals to 0, which is equal to c1 plus c2 times 0 plus c3 times 0 squared. So these two terms are gone because of zeros, and we basically find out that c1 is equal to 0. Okay, so that's a good starting point. Next, let's go to boundary condition 3. And I'm going to boundary condition 3 because I think it's easier because, as you can see, u of y is equal to 0, and I feel like just it's easier to work with than boundary condition 2. So I'm going to start off with this one first. Okay, so we have u of y equals to 0, which is equal to, c1 is 0, so I'm not going to write it here. That would be c2 times b plus, this would be c3 times b squared. Okay, so then we can basically create a relationship for these constants. So if we did something like c3 equals to negative c2 over b, we'll come back to this because technically we need our last boundary condition to figure out what these constants are, but this is a relationship that we will develop for now. Let's go to boundary condition 2 now. And for this, we have u of y is equal to u max, which is equal to c1 is 0 plus c2 times y, which is b over 2 in this case, plus c3, which technically we can plug this value in of c3, this relationship, so that would actually be negative c2 over b times y squared, which would be b over, actually, excuse me, yeah, b over 2 squared, just like that. And from there, basically, after you simplify all of this out, do I want to skip this? I don't know if I want to skip this step or not. I feel like this should be pretty straightforward, so I am going to skip it. But basically, you can find that C2 is just going to be equal to 4 times U max over B. And there's nothing really complex I'm doing in this last step here. It's literally just math because C2 times B over 2 plus, or I should say minus C2 times B over 2, B over 4, excuse me, you'd end up with this final solution here. So you just simple algebra. So we have C1 and C2. Now we can actually plug C2 back into this relationship for C3, and we can get that C3 is just going to be equal to negative 4 times U max, all divided by B squared, which then gives us a final velocity profile here, U of y, is equal to, let's plug it in, C1 is 0, C2 would be 4 times U max. I'm just going to put UM for now, but UM equals to U max, just so I can reduce some of the writing here. So that would be this times Y minus 4 times U max over B squared times Y squared. And we can simplify this even further by taking out 4 times U max. This would be equal to Y over B minus Y over B quantity squared, just like that. And that's our velocity profile there. So after this, let's go to the next page and kind of refresh everything. So U of Y is equal to 4 times U max Y over B minus Y over B squared. Okay, and similar to our previous part A, we did this thing where we took our kind of global constraint of mass flow rate at surface 1 and set it equal to kind of the definition of mass flow rate, which is just rho times V times A. And we're going to do the exact same thing now for this part, but because velocity is not uniform, we have to actually do some integration. So mass flow rate of surface 1 is going to be equal to our integral, and our integral here would be from 0 to B, rho, and our velocity would be U of Y. So I'm going to plug that in. Actually, hold on, let me just do a parentheses here. Lots of math writing here. And then our area here, and remember this is actually per unit width, mass flow rate per unit width, so our area would be dy, or integrand area that we're integrating over because we're changing with respect to y here. Okay, and then we just solve this integral. So this would be equal to, technically our rho times 4u max can come out of our integral. So be y over b minus y squared over b squared dy. My hand's starting to cramp now. I gotta get a better tablet for this in the future. So m dot 1 per unit width is equal to rho times 4 times u max. And when we do this integral, we get y squared over 2b. This would be minus y cubed over 3b squared. And we're evaluating that from 0 to b. And that's going to be equal to 4, or rho times 4 times um. That would be b squared over 2b minus b cubed, excuse me, my phone was ringing there, over 3b squared. Let's see, our b can cancel down here. These two can cancel. This is excessive amount of writing right now, but I'm just going to do it at this point because we're almost done. So be b over 2 minus b over 3. 1/2 minus 1/3 is 1/6. So this is equal to rho. 4 over 6 is just 2 over 3. Just like that. And now we can set this mass flow rate equal to our global constraint mass flow rate, which, if we recall, our global mass flow rate that we found was just equal to rho times L times V plate. So we set these two equal to each other. and we can actually solve directly for the maximum velocity of our parabolic velocity profile. So rho LVP equals 2 over 3 rho U max. That's a really bad M. Times B. Our rows will cancel on both sides, and you finally are left with U max is just equal to 3 over 2 times LVP all divided by B. Okay, that's it. You made it. So there's a lot of weird things that happen in this question, especially when you get to like the parabolic velocity profile. I mentioned before that one of the big sources of confusion is kind of seeing this link here where you develop kind of like a global constraint of mass flow rate based on the plate coming down with some velocity, and then you set it equal to the mass flow rate at a single surface. And, some people just don't think to equate those to each other, but you definitely can do that. And that's how you would actually solve for your max velocity. Now, with the uniform profile, again, our maximum velocity is one single value because it's equal across the entire face. But with our parabolic velocity profile, we had to actually integrate when we used our mass flow rate equation here. So yeah, that wraps up conservation of mass. And if you are kind of getting to the end of this and you're like, well, this was literally just pure math, you're correct. Conservation of mass and conservation of momentum are actually very simple. The math and the integration and signage and things like that are what causes people to get stuff wrong. So as long as you're very diligent about your math and you know the fundamentals very well, you'll get pretty much, 90% of your points on an exam, depending on what kind of professor is grading it. But yeah, that's it. So please stay tuned for the next video if you're curious on conservation of momentum. And then we'll do some other fun practice problems associated with that. Thank you.